Hi friends, in the last video we've seen what are semiconductors, right? In this video we'll see different types of semiconductors, that is intrinsic and extrinsic semiconductors. What you're seeing on the screen is the structure of silicon. Of course, germanium also exhibits the same structure, that is tetrahedral structure. You see that each silicon atom has four bonds. You can call them valence bonds or covalent bonds. But this structure which you are seeing, that is the perfect structure which is exhibited only at 0 Kelvin, that is absolute zero, at that temperature only. Uh, if temperature increases, what happens? You see that there are four outermost electrons or four electrons in the outermost orbit of silicon atom. So it has four covalent bonds, one electron from this silicon atom and other from this silicon atom form a bond. Similarly, here also happens and there are four bonds, right? Now, as temperature increases, more thermal energy becomes available for the electrons. So they break away and become free electrons. So say this electron becomes free of the influence of these atoms. And if that electron is free, and that electron is what we are interested in, because that is a conduction electron. Since this electron is free to move, that movement of charge is nothing but charge transfer, and hence we get electricity, right? So for current, we need free electrons. And one more thing, if this electron gets away, here there is a hole. Observe that. That is a vacancy. Although hole is not a particle, it is treated as a charged particle with effective charge plus C. That is equivalent to a positive charged particle with same magnitude as the charge of electron. Now, why am I bothered about this hole? Because electrons can give us current, right? Because of their movement. These holes can also give current. Say this electron got excited and here there is a hole. But there is an electron here, right? And it can go here like this, in this way. So what does it mean? So the bond here completes, but here there is a hole. Observe that. And again what happens? The electron here may come here. And again here there may be a hole. So it is equivalent to say that hole is moving. Actually it is not the hole moving. It is the electrons that are moving to the places where the holes are there. But effectively you can say that the hole is moving. And movement of electrons is giving you what? Current, right? Here also electrons are moving in this way, right? In the opposite way. It is equivalent to saying that hole is moving in this direction. So effectively there is current here also due to the movement of charges, that is movement of electrons or movement of holes. Actually, motion of hole is only a convenient way of describing the actual motion of bound electrons. That's it, observe. And note one more thing. Because this is a crystal made of only silicon atoms or one kind of atoms, only electrons are ejected or given out by these bonds only, right? So if one electron is ejected, there is a hole. So I want to say that the number of electrons, number of free electrons or conduction electrons will be equal to number of holes for intrinsic semiconductors. That is what is the main point of this intrinsic semiconductors. Intrinsic means they are made of only one type of material, that is silicon or germanium, or only one kind of atoms. Ni is the intrinsic carrier concentration. Maybe that carrier may be hole or a free electron. This is a general term. Now, movement of free electrons gives us some current, right? Let that be IE due to the conduction electrons. And movement of holes also gives us current. Note that a hole is also a charged particle with effective charge plus positive charge plus Q. Okay, so let that be IH, current due to the holes. The sum of these two, it will be the actual current inside this intrinsic semiconductor. Let it be I. Hope everything is clear. Now, when electrons are moving freely, they may encounter holes created by ejection of other electrons, right? So there may be a recombination. So what? Number of free electrons and holes will be decreasing. But since thermal energy is provided by temperature, similarly some generations are also taking place in somewhere, in some other place. So there is something called as equilibrium. At equilibrium, rate of generation of charge carriers will be equal to the rate of recombination of charge carriers. And this is about intrinsic semiconductors. But Normally, silicon and germanium exhibit these characteristics. Why not carbon? Carbon also has 4 electrons in its outermost orbit, but it doesn't exhibit semiconductor properties because even that exhibit tetrahedral structure, but the outermost electrons are in second orbit of carbon, whereas in silicon they are in third orbit because silicon is in third period of periodic table, right? And for germanium it is fourth orbit. So these electrons for germanium are far away, fourth orbit, far away from the nucleus. So removing them is easy, and it is less easy but easy for silicon because they are in third orbit, whereas in the case of carbon they are near to the nucleus, so removing them is very difficult, and hence even if you give some thermal energy, not much or not appreciable number of electrons are ejected, and hence the conductivity will be very less. So carbon acts as insulator. For that matter, silicon and germanium also act as insulators at very low temperature, because finally the logic is this one. You need to give thermal energy either through temperature or by heating to eject electrons. Here it is easy, here it is difficult. That's it. The problem with intrinsic semiconductors is that the number of charge carriers are very less, even with silicon or germanium also. If you use only one kind of material, the number of charge carriers are very less. And other limitation is that the conductivity or the number of charge carriers mainly depend on the temperature. So, say if you have a calculator, it shows one value for 2 plus 3 in winter, and it would have shown some other value in summer, because in summer the temperatures are more, so the conductivity varies of the materials or wires, whatever circuits. So more current, and hence you get different values. That is one more limitation. Actually, in olden days, there were calculators which were not working in sunlight. The reason is this one. So nowadays, we have something called as extrinsic semiconductors, and there we do something called as doping. Doping is just adding an impurity. Because of that impurity, the number of charge carriers are increased to a very high extent actually. And of course, the impurities are added very little, that is maybe few ppm, parts per million. So because of these impurities, the conductivity of intrinsic semiconductors becomes very high even at room temperature. So these can also be called as impurity semiconductors, and those impurities are called as dopants, and that process or addition is known as doping. Now, how to choose a dopant? Actually, when you add a dopant or when you add an impurity, the crystal structure shouldn't change much. It should not be what? It shouldn't distort much. So when is it possible? It will be possible if the size of dopant will be comparable or nearly same to the size of actual atoms. That's why we take those elements which are present nearby or in nearby groups to this one. This is fourth group, right? Silicon and germanium are present in fourth group. So we take those elements present in third group as well as fifth group. When you take atoms from this group, though those are trivalent impurities, and when you take atoms from this group, here they are pentavalent impurities. So here also there is a classification, or there are two types of extrinsic semiconductors. When you add a pentavalent impurity, say phosphorus here, then it is known as N-type. The atom which is acting as impurity here has what, plus 5 valency, right? So it has 5 outermost electrons, and 4 of them are bonded with silicon atoms in a normal way, regular way, like the silicon atoms do, but there is 1 electron left out. So that fifth electron remains weakly bound to its parent atom, and hence the energy that is required to take out this electron, that is ionize that electron, will be very less, and hence with very little energy we are able to get a free charge or conduction electron. So this pentavalent dopant is giving out one electron, right? It is donating one electron. That's why it is called as donor impurity. And the number of electrons available for conduction by these dopants, they depend on the doping level and of course temperature also. So if Ne is the total number of free electrons, that is conduction electrons that are present in the crystal. Now NH be the number of holes. Even holes will be there due to the ejection of electrons by temperature, that is thermal energy, like we discussed before. Even here holes will be there, but number of free electrons will obviously be greater than number of holes, right? Actually they will be very larger than holes, and hence you have negative charge domination. Observe that. That's why this is called as n type. Here electrons are the majority carriers and holes are the minority carriers. And similarly we have another type of extrinsic semiconductor. It is p type. When we dope the crystal with a trivalent impurity, this atom has 3 electrons in its outermost orbits, right? So using those 3 electrons, it forms bonds with the surrounding silicon atoms, 3 of the surrounding silicon atoms. But with the 4th silicon atom, it doesn't have any electron, right, to bond. So there comes a hole. And similarly, here the total number of holes are the holes generated by this dopant, as well as the intrinsically generated holes. And electrons are even generated here, but these are generated only by supplying thermal energy, that is rising temperature, right? And obviously here the holes will be dominating, very larger than number of free electrons. Here it is positive charge, that is holes, that are dominating, right? So that's why it is called as p type, p for positive. And note that crystal always maintains charge neutrality, like see in this case, even though it is giving one electron, if it gives away, there is a positive charge, that is this ion turns into a cation, right? So minus and plus, the charge is always balanced. Even here also this atom is giving only 3 electrons, it's not giving any electron here, and hence it has only plus 3, whereas here since they are giving 4 electrons, they have plus 4. So the crystal is always neutral, whether you have dopant or if you don't have dopant, it doesn't matter. But there is one thing I need to tell you. For extrinsic semiconductors, if Ne is the number of free conduction electrons and NH is the number of holes, the product will be equal to Ni square, where Ni, as I said before, is the intrinsic carrier concentration. And note that this result is only approximate and hypothetical. Let us solve this problem. Suppose a pure silicon crystal has 5 into 10 power 28 atoms per meter cube. Okay, it is doped by 1 ppm, 1 part per million concentration of pentavalent arsenic, and calculate the number of electrons and holes given that Ni, intrinsic carrier concentration, is given as 1.5 into 10 power 16 per meter cube. Well, you know this formula, right? Ne into NH is equal to Ni square, we just discussed now. We are assuming that the number of electrons generated thermally is very small because this is pentavalent impurity, right? So n-type semiconductor we are going to get, and majority of the electrons are given by these things only. So we are assuming that the thermally generated electrons are very less in number, and hence we can say that the Ne concentration is nothing but it's given by these dopants only. So the concentration of dopants will be equal to 10 power 28 into 5 is the concentration of total atoms, but 1 part per million. So divided with million. This will be the concentration of the electrons, that is free electrons, that is 22. Okay. So my number of holes NH will be 1.5 into 10 power 6 Ni square of it. So 2.25 into 10 power 32. Sorry, this is 16. I read the question wrong, I guess. So it is divided by Ne, that is 5 into 10 power 22. That will give you the number of holes as 4.5 into 10 power 9 per meter cube. This will be the concentration of holes, number of holes per meter cube. That's it for now. In the next video, we'll see what is a PN junction and also what is a diode. It's going to be interesting. Keep watching. Bye.